What's up, explorers, and welcome back to the channel. I'm Burkay, and today we are venturing out hundreds of millions of miles from Earth to the edge of the solar system, to a place that might just change everything we think we know about life in the universe. We're not talking about Mars. We're talking about Saturn's tiny, brilliant, icy moon, Enceladus.
Hey everyone, and Burkay, it's hard to overstate how special this moon is. Visually, it's stunning. It's one of the most reflective objects in our solar system, almost pure white. But that's just the cover of the book. Picture this, a world smaller than Texas, completely wrapped in that brilliant ice, but hiding a profound secret. Beneath that frozen shell lies a global ocean of liquid, salty water, and it doesn't just sit there. It is so active that it erupts violently into space.
Exactly. It literally blasts these massive geysers or plumes of its own ocean out into the void through huge cracks in the ice they call tiger stripes. Think about that. For most of space exploration, we have to send landers and drill deep to find clues. Enceladus is practically begging us to study it, handing us a free sample of an alien sea. And today we are digging into a study that just dropped, which took some of that old data and found something that, well, it's a complete game changer. This has completely shaken up the search for life.
It's almost like scientific time travel. The data comes from NASA's legendary Cassini spacecraft, a mission that gave us so much, which ended its journey years ago. Specifically, the data is from one single super-fast flyby that happened way back in 2008. It's an incredible story of discovery hidden for nearly 2 decades.
Which brings up the big question, right? This data is 17 years old. In science, that's an eternity. We've had entire missions start and finish in that time. So why are we suddenly getting these revolutionary results now? Was this incredible information just hiding in plain sight the whole time?
In a way, yes, it was there, but we couldn't read it properly. And the key, the secret ingredient that finally unlocked it all, was one thing: pure, unadulterated, breakneck speed.
Okay, you have my attention. How fast are we talking?
We're talking absurdly fast, nearly 18 kilometers per second, which is over 40,000 miles per hour. To put that in perspective, that's fast enough to fly from New York to Los Angeles in about 4 minutes. It's a speed that makes a rifle bullet look like it's standing still. For context, most of the other times Cassini sampled the dust around Enceladus, it was going at a much more leisurely pace, maybe 9,000 to 27,000 miles per hour. This one flyby, called E5, was just built different.
And I love this part. It was a complete accident, an amazing fluke. The crazy speed wasn't planned for some brilliant chemistry experiment. It was just a consequence of orbital mechanics needed to get the spacecraft on the right path for its next objective. It was pure, beautiful serendipity. But hold on, my first thought, and probably a lot of yours, is wouldn't hitting an ice grain at 40,000 miles per hour just obliterate it, pulverize it into nothing, make it harder to read the signal, not easier?
That's the totally counterintuitive genius of this discovery. You're right to think that. At the slower speeds, when an ice grain hits the detector, the water molecules kind of get sticky. They clump together during the impact and ionization process, creating this huge, messy electrical signal. Think of it like trying to hear a tiny pin drop during a massive heavy metal rock concert. The water is the deafening sound, a wall of sound that completely drowns out the faint, subtle signals of any other interesting chemicals mixed in. The instrument was effectively blinded by the very thing it was trying to study.
Okay, I see. The water signal was just too loud, creating a sort of chemical static. So it happened at 40,000 miles per hour. What changed?
The rock concert suddenly went quiet. The impact was so energetic, so unbelievably violent, that the water molecules were instantly atomized. They were shattered and ionized in a totally different way. They didn't have time to form those big, noisy clusters. The background noise from the water dropped to almost nothing. And for the first time, hiding in that 17-year-old data, the faint whispers of complex organic molecules just popped right out. They were finally audible, clear as day.
That is genuinely one of the cleverest things I've heard in a long time. The speed wasn't a bug, it was a feature, a happy accident that acted as a chemical filter, letting them see what was physically impossible to see in all the other slower samples. My mind is just blown by that. We're finally seeing the ocean's true chemical inventory, totally unmasked.
And what an inventory it is! This wasn't just finding a few more molecules. The study confirmed some things we suspected were there, but it officially revealed 4 completely new categories of organic molecules that are crucial for life. We're talking basic carbon and hydrogen chains, called aliphatic compounds, the simple Legos of biology, more complex ring structures, some involving oxygen. Think more advanced chemical architecture. Things called esters and ethers, and the big one, the headliner, compounds containing both nitrogen and oxygen.
Let's park on that for a second. The esters and ethers are a huge clue in this detective story because they hint at how these molecules were made. Scientists believe they were likely cooked deep inside Enceladus, in the crushing pressure and high temperatures where the global ocean meets the moon's hot, rocky core. It points directly to hydrothermal vents, just like the ones we see at the bottom of our own oceans on Earth, places that are teeming with life totally cut off from the sunlight.
Exactly. It suggests this ocean is a dynamic, chemically active environment powered by the moon's internal heat. It's not a stagnant pond, it's a planetary-scale chemical factory. But Burke, let's get to the discovery that made every astrobiologist on the planet sit up straight. That 4th category.
Oh, absolutely. This is the moment the story goes from interesting to history-making. For years, the Holy Grail has been finding amino acids, the building blocks of proteins. But this study found evidence for something that gets us even closer to the instruction manual for life itself.
They found derivatives of a molecule called pyrimidine. Now, that might not mean much to you at first, but it absolutely should. Pyrimidine is the core structural backbone for 2 of the 4 letters, the nucleobases, in our own DNA, cytosine and thymine, and for 2 of the letters in RNA.
Let that sink in for a moment. They didn't find DNA. Let's be crystal clear about that. But they found compelling evidence for the factory that makes some of the most critical, irreplaceable parts for it. It's like exploring a new planet and not finding a car, but finding a highly specialized factory that manufactures engine blocks and transmissions. You know something incredibly complex and functional is being built there. We're talking about the potential for genetic material.
It's a massive leap forward. So let's run through the official checklist for a habitable world. Liquid water? Definite check. An entire global ocean, confirmed salty and teeming with minerals. An energy source? Check. Strong evidence for those deep-sea hydrothermal vents providing heat and chemical energy completely independent of the sun. The right chemicals? Big, bold check. With this new analysis, we now have confirmed evidence for 5 of the 6 essential elements for life as we know it. Carbon, hydrogen, nitrogen, oxygen, and phosphorus, all spewing directly from that ocean. The only one we haven't officially seen in the plumes is sulfur, and scientists are pretty sure it's in the rocky core.
The recipe for life is practically complete and just sitting there. And this is why this study is so important. It provides the strongest, most direct justification yet for a new dedicated mission to go back. This isn't just a hunch anymore. It's a scientific roadmap pointing to a specific destination, and it's telling us that Enceladus is one of the most compelling places to search for life beyond Earth.
Which sets up a truly profound question, maybe one of the biggest we can ask. What happens if we go back with a dedicated mission, one designed specifically to find life, and we find nothing?
That's a thought that gives me chills, in a good way. It's a staggering philosophical point. If you have a place with liquid water, a source of energy, all the right chemical ingredients, and it's been cooking for potentially billions of years, and life still doesn't arise, that would tell us something fundamental about how impossibly rare and precious life on Earth really is. It would mean that the spark of life isn't an easy, inevitable outcome of chemistry, but something far stranger and more wonderful.
It's a can't-lose scenario for science. Either we find that we are not alone in the universe, or we find out that the barrier to get life started is far higher and more mysterious than we ever imagined. Either way, our understanding of our place in the cosmos changes forever.
So, there you have it. A 17-year-old secret hidden in the data of a legendary mission unlocked by a happy accident of speed. Enceladus isn't just an icy moon anymore. It's a dynamic chemical reactor making molecules that are directly relevant to you, me, and every living thing on this planet. But now, we want to hear from you. What do you think is the biggest clue from this discovery? For me, it has to be the pyrimidine derivatives. That just feels so close to the blueprint of life itself. But what about you? Is it the evidence for hydrothermal vents? Or just the sheer abundance of all the right ingredients? Let us know your theories in the comments section below.
We love reading your thoughts. And if you enjoyed this deep dive into the Enceladus enigma, do us a huge favor and hit that like button and subscribe to Berkay Explores so you don't miss our next adventure.
Thanks for exploring with us. Keep looking up. We'll see you next time.